the topological entanglement entropy is not something that you can measure trivially in an experiment. Indeed, actually, entanglement entropy is something that we use extensively in the theory community to talk about phases of matter.
I hear there's a measure of entanglement, or an entanglement witness, that someone here is an expert on, that can be used in experiments, or can be observed in experiments.
Yeah, that's right. So there's thank you for teeing me up actually to talk a bit about my research here. So as it turns out, there are many different ways of looking at quantum information theory. So in classical information, we have this concept of the Shannon information, or the which basically in the physics business, what we call entropy is a sort of special case of the Shannon information. And one way of describing the Shannon information is that it's a sort of measure of how unpredictable a probability distribution is. So if I give you a distribution and it's really hard for you to guess what the next value of that distribution is going to be, then the Shannon entropy of that distribution is high. Whereas if I give you a process that is totally deterministic, the Shannon entropy is 0. And so a pure state wave function, even though it has randomness to it, even though quantum mechanically there is randomness to a pure state, the generalization of the Shannon information for a whole pure state is 0, because the pure state technically contains all the details about the system. It contains all the information you could ever want to know about it. But if I look at a subsystem, right, this is where the entanglement entropy kind of comes from. If I look at a subsystem, then the fact that subsystem is entangled with the part of the system that I'm not looking at means that it becomes somewhat unpredictable to me, because I'm not looking at the entire system as a whole. The whole is sort of more than the sum of its parts. Because I'm not looking at the entire system as a whole, I'm just looking at this subsystem. The results of measurements are going to be unpredictable in a way that is sort of classical. It's sort of like the Shannon entropy. And so that's what the entanglement entropy is really a sort of measure of. Well, there's another quantity in classical information theory, which is basically the second derivative of the Shannon information. It's a quantity called the Fisher information. And it basically measures, if I give you a probability distribution, and say I give you a coin, and the coin has a particular weighting to it. So maybe it's heads or tails, but the probability of heads isn't 50-50. The probability of heads is 60%. And I imagine that the probability of heads is a sort of parameter I can tune. I can ask the question, how easy is it for me to distinguish a coin that is weighted 60% heads from a coin that is weighted 61% heads? And the speed with which my ability to distinguish those two coins changes as a function of the weighting is the Fisher information. So it turns out that in the quantum world, quantum states are made more distinguishable from one another by the presence of entanglement. So if a quantum state is extremely entangled with respect to a certain measurement that I'm making, it's much easier to distinguish. If you imagine maybe I have a quantum state, and maybe that quantum state depends on some underlying parameter, theta. If that state is extremely entangled, then there's a sense in which it's easier for me to distinguish theta from theta plus a small little change in theta. And it's been demonstrated that this quantity relates directly to what's called genuine multipartite entanglement. So in other words, when we talk about the sort of standard von Neumann entropy story, we imagine I give you a wave function and I say to you, factor the wave function. So factor the wave function into a wave function on system A times a wave function on the complement of A. And if you can do that, then A and the complement of A are not entangled. And if you can't do that, then there is some entanglement measured by the entanglement entropy. But what if I want to do this problem, what if I give you 50 subsystems or 100 subsystems? What if I'm talking about a system that has millions of particles and I want to know how entangled each individual particle is with each other particle?
I see.
Sort of genuine multipartite entanglement.
The
Fisher information measures that and can be detected through response functions. And so an area that I'm extremely interested in at the moment is looking at different ways that you can use the Fisher information, which is experimentally accessible directly, to probe the entanglement structure of these topologically non-trivial ground states. And so I think this is a very interesting and much work has been done. I should say that much work has been done on this. There's a great paper. I think it's actually called Multipartite Entanglement of Topological Phases, and I wish I could recall the names of the authors. Maybe someone watching will be able to pull it up. Worth a read, and they sort of do a very nice theoretical study on how the Fisher information for various. There are some technical details that one has to think about when looking at the Fisher information, but they basically study how the Fisher information responds to different topologically non-trivial phases. And so inspired by that work, I've also done some work, published some work looking at a model, again by Alexei Kitaev, a model that has a topologically non-trivial ground state in one of its two phases, and how the Fisher information behaves at the interface between these two phases, and whether we can say anything about topological order. And so, yeah, that's a major area of interest for me, certainly.